All right, so the example that we are doing today is 2:1 mux, and the mux design that is given to us has one select input, and we name that A. F is your output, and when the select line is 0, which means A is 0, F equals B complement, and when A is 1, F equals B. So by looking at this 2:1 mux design from the symbol itself, you can write these two statements. If A equals 0, F equals B complement, and the other statement is going to be when A equals 1, F equals B. So that's exactly what this symbol means in terms of statements. And you can translate these statements into a truth table very quickly. So for example, you can say this guy is A, this guy is B, those are my two inputs, F is my output. And if I have two inputs, I can have four possible combinations between them, 0, 0, 0, 1, 1, 0, 1, 1. And for the first two, A is 0. And when A is 0, F is B complement. So I should flip B, 1, 0. And for the next two, A is 1. Over there, F equals B. So 0, 1 remains as 0, 1. And once you have this truth table, you can take a look at what the outputs are doing. F now is simply A complement and B complement, or A and B. In other words, it is exclusive NOR operation between the two inputs A and B. So that's exactly how you would answer that question. So that was the question that you saw on the quiz. Now let's try to see if we can implement a two input AND gate using a 2:1 mux. So again, we are trying to use the same Shannon's expansion that we saw last time to answer this problem. So I'm going to box this up so that I have that as my reference. And then I'm going to say, all right, let's start with a truth table for, not even a truth table. Let's start with an expression for AND gate. Let us suppose I have the inputs as A and B, right? That's it. That's the expression for an AND gate. Now, if I want to use Shannon's expansion, then I need to write the same expression in this form. A ANDed with some logic function, or A ANDed with another logic function, such that all of this becomes the top input to the 2:1 mux, and all of this becomes the bottom input to the 2:1 mux. Now, in order to establish that the second equation is the same as the first equation, I need to fill in those square brackets with logic expressions. So clearly, in F equals A and B, there is A, but there is no A complement, which means a 0 would go in here and a B would go in here. So if I do that, then both of these expressions are equal. So I'm not changing F by any means here. And that's it. This would become my top input, and this would become the bottom input for the 2:1 mux. So I can quickly go now to the symbol and say A, B, F equals A and B. It is equivalent to a mux based design where you have the select line as A, and when A is 0, your input is the top input, 0. And when A is 1, your bottom input goes through, which is B, and that would be F. That's it. And then you can use the truth table to verify this, right? You can quickly put out a truth table for AND gate and say, all right, 0, 0, 0, 1, 1, 0, 1, 1. F is going to be equal 0, 0, 0, 1. That's the truth table for AND. Let's see, let's move this up top. And if I want to see if they are equal or not, when A is 0, F equals 0. Let's see. When A is 0, F equals 0. So that checks out. And when when A is 1, so F is B. A is 1, 0, 1, 0, 1. F is B. So that's how you can quickly verify whether you are on the right track or not. Okay, let's move on here and talk about a summarization for the MUX. MUX are essentially data switches. So if you have a many-to-one switch, in MUX's multiplexers or multiplexers can be used to select one out of those data inputs or data sources. Each data source could be 1 bit, or they could be multi-bit data sources as well. We have seen the examples of both situations earlier. That's point number 2. They can switch one or more bits. They are essentially used for routing incoming data to a selected output. So many to one. I have many inputs coming in. I need to route one of them to a particular selected output. That's why I would use a multiplexer. And what makes it really, really useful is that they can also realize arbitrary logic functions. Now, if you go and take a look at your studio, the VHDL studios, and if you go and dig in to the LED display, component that you used for previous studios, you will see that there is a lot of MUX implementation in that particular component. So MUX is what I'm trying to derive at is a MUX is a very, very useful component. Just as the decoder is, because the decoder can also be used to synthesize logic functions. And we also saw earlier that NAND and NOR gates can help with that as well. All right, now if there is a MUX, there is a demux, right? The counterpart of a decoder was an encoder, and the counterpart for a multiplexer is a demultiplexer. So in this case, we are going from one to many. So route one input to one of the selected outputs. So you can talk about demuxes as distribute data from one source to n inputs. So based on the select line, the input may go to the first output or the second output or the third output and so on. So it's exactly the flipped version of the mux. They too can switch more than one bit, just as the multiplexer. All right, so let's see this demultiplexer, which is the opposite of a mux. You have a single data input. Earlier, you had a single data output. Now you have a single data input with n control inputs or n select lines. And in this case, you have 2 raised to n outputs. Earlier, we had 2 raised to n inputs. The control input, also called as the select line S, represents the binary index output to which the input is connected. So let us try to see if we can sketch out a simple demultiplexer here. So let's see here. Okay, I'm going to use red to do this. I'm going many to one, so my trapezoid faces the other way. it tapers to the right. Sorry, that was multiplexer, right? Now I have a demultiplexer. So I have small here, and then it goes to many outputs. So I've got one input here, and this can be many outputs. Let's say for this example, I select 4 outputs. And if the number of outputs of a demux are 4, I would definitely need 2 select lines for this. So I'm going to draw the 2 select lines right here. And let us use some other color for naming them. Say my input, I'm going to call the input say I, and I have my 2 select lines. S1 is the most significant select, S0 is the least significant select. And let's call the outputs O1, O2, O3. Oh, well, let's start with 0. O0, O1, O2, O3. So that would be 1 to 4 demux. So one input comes in, one data source as the input, it could go to one of the 4 outputs based on the select lines. So let us characterize this in the form of a few statements. So the statements would be if S1, S0 is 0, 0, both of them are 0, 0, then O1, O0 is going to be the input I. When S1, S0 are 0, 1, O1 is now going to be the input I. S1, S0 as 1, 0, this implies that this third one is going to be the input, and when S1, S0 are 1, 1, that implies that O3 is going to be the input I. So you can think of this as based on the 2 select lines, this guy could go here or here or here or here, right? 4 different paths for it, and all it depends on what S1 and S0 will be. Now the question is, suppose we are in this condition. Suppose we are here. We have made S1 and S0 as 0, 0. We know that, let's see, it is, right? That's what is happening now. Output O0 is equal to the input I. But what about the rest of the inputs in this case? The rest of the outputs, O1, O2, O3, what are they then? What do you think they should be? So as you can see, they are not high impedance in this case because I have not put an enable, right? I have not disconnected it out. So in some demultiplexers, it could be completely disconnected where they become in high impedance state. But in a very, very simple design of demux, they will all be zeros. So in a simple design, they will be zeros. Simple design, outputs are low. But in a slightly more complicated design where you have an additional switch controlling whether they are dangling wires or not, if you have that, then those will be in high impedance. I will elaborate on that point a little bit more by when you take a look at the inside of this simple 1 to 4 demux. So this is, I'm claiming that this is a 1 to 4 demux. So essentially the design, this, right? Whatever we designed here, the insides of that are presented over here. So for now it is a claim that this is it, but let's try to see if that is the case or not. Now the input I goes to all the AND gates, right? So I is the same as I is the same as I is the same as I, and you can actually pull this out. I, that's the input. Then you have two select lines. The two select lines are S1 complement, S0 complement. The two select lines are S0 and S1. But for the first AND gate, you have the complemented versions. The second AND gate, you have S1 complement S0. The third AND gate, you have S1 S0 complement. The fourth one, you have S1 and S0. So let's try to take a look at this. What would happen if S1 is 0 and S0 is 0? What would happen then? Well, only this guy will equal I, but all the others will equal 0. Right? Because these guys, both the inputs of the AND gate need to be 1 in order for that particular input to go through. And that only happens over here for the first AND gate, because S1 is 0 and S0 is 0. And as you go down this list of 0, 0, 0, 1, 1, 0, 1, 1, that will switch to O1, O2, O3, and that's it. So that's how you would implement a simple 1 to 4 demux. Now on top of that, if you had an additional switch here, so let me show you what that. If you had an additional switch, let's say I have, right, and then I say this is enable. If I had something like that where I was controlling whether the in this guy I can connect to O0 or not, if I had a tri-state buffer over there, then the outputs could be in high impedance state. Or I could also control this in using a simple switch like this. Right, and then I can say this is my enable. So it could be like a simple toggle switch, or it could be a tri-state buffer, whatever that is. That is the additional functionality for this demux. So the outputs could be zeros in that simple design, and they are still a part of the design here, or they could have 4 of these switches here, 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 and here to go to that high impedance output. Yes. So I would say I am going to make this enable depend on the select lines. So if the select lines were 0, 0, I would make this enable active, all the other enables inactive. So yes, the enables would depend on the select lines. Why is O0 I and the other? Okay, so here, let me erase this guy, bring this here. And let me erase this. So the condition that we are looking at is this. S1 is 0 and S0 is 0. So only in that case, what would be S1 complement? Well, S1 complement would be 1, S0 complement would be 1. So what would the output be? It would be I and 1, which is I, right? But over here, if you go down, what will you have over here? S1 complement will be 1, but S0 will be 0. So you get I and 0 and 1, which is 0. And so on. That all the others will go to I and let's see, 0 and 1, 0. No problem. All right. So that was the discussion on demux. Let us move ahead and take a look at some block diagrams or symbols. The top ones are equivalent switch block diagrams. So on the left you have a multiplexer, on the right you have a demultiplexer. So as you can see here, the first diagram or even the second diagram, we are showing how we could take multiple sources. In this case, you have 26 sources, source A, source B, source C, all the way to source Z. You are selecting one of those sources using the source select. Whatever source you select, that information goes on the bus to the demultiplexer. And then if that needs to go to a destination, one of the 26 destinations, then you have a destination select. So you could go from any to any by selecting the source select and the destination select lines. You guys see that? So many to one, one to many. So you can use this as selection and distribution of data. So that's a switch equivalent, as you can see here. Also note that if I tell you the number of sources on this side, you directly know the number of bits for the source select. How many bits would you need for source select? All right, so Alex says 5. And I'm hoping that his answer maps to the destination select as well, because there's again 26 destinations too. Absolutely right. 2 raised to 5 is 32. We have 26 of them here. We have 26 of them here. You can't stop at 4 because you only cover 16. You have to go one more. So you have to go 5. That's absolutely right. And again, each of these sources, A, B, C, and so on, they could be 1 bit, they could be multiple bit. It doesn't matter. No matter how many bits they are, you still need 5 bits for the source select and 5 bits for the destination select. Now let me ask you this. If sources are 4-bit each, so each of these sources, source A is 4 bits, source B is 4 bits, source C is 4 bits, and so on up to source Z is also 4 bits. What would be the width of the bus? Absolutely, it has to be 4 bits, because one of these guys needs to go through that bus. So if this is 4 bits, that has to be 4 bits, which also means each of these has to be 4 bits as well. In terms of switches, yes, you would need 4, but you see, you can obviously treat this as a 4-bit mux, right? So it depends on what type of mux are you using. If you are using a mux which has inputs that could be multiple bits, then you will be fine. For example, earlier, let's see, I'm going to take you back to, I guess, this guy. This was something that we looked at last time, where there was a chip 74157 which had 4-bit inputs and 4-bit output. So it really depends on what type of mux you have available to you. All right, let's move on. Go back here. Okay, so whatever that top block diagram was, which was essentially an equivalent switch here, switch is being used for mux and demux. So a commutator picking one of the sources and delivering that information to one of the destinations. Now, in the second one, we are essentially representing that same thing using the symbols for a mux and a demux. So for a mux, you have a trapezoid with the long side representing the many inputs and the short side representing the one output. Again, you have the source select lines to pick one out of the 26 input sources or data sources, goes through the bus. Same strategies, same analysis as before. And then you have the destination select for the distribution of that bus data to one of the destinations. Uh, let's see. You guys are talking about uh, 4 individual switches. So for each, right? If this is 4 bits, and if you want to go down and represent each of them as a switch, like a commutator like this, then you would have one switch here, one switch here, one switch here. So you would have 26 switches, and each switch could be in one of the 4 positions, right? So you would have 26 switches there. We talked about this earlier. I'm going to just refer to you over there. Let's see right here. So as you can see, this was the same diagram where you have the number of switches are 1, 2, so on up to B. What is that B? B is each data input is B bits. So in our case, if you have 4 bits, you would have 4 of these, 1, 2, 3, 4, and they would have 26 positions. So you can design that multiplexer as that 4 switches, each switch that could be in one of 26 positions, or you can have 26 switches where each switch could be in one of 4 positions. So the design varies. You can have this the right design both ways, but choosing 4 switches might be very efficient. 4 switches, each switch is one of 26 positions. Okay, so that's how you would represent them in the form of block diagrams. Now let us try to take a look at an interesting example here. We are trying to use a 3 to 8 binary decoder, and that decoder is right here. Note over here that all for the 3 to 8 decoder, all inputs and outputs are active high here. And the claim is that I can use a 3 to 8 decoder as a 1-bit 8 output demux. So I'm going to try to use this as a 8-bit 8 output demux, meaning 1 to 8 demux, where each line is only 1 bit. So let us see how this goes. I'm going to try to show you guys what the left diagram indicates. The left diagram indicates that you have an enable which is essentially connected to the source data. So tell me what happens if the source data is 0 or 1. If the source data is 0, the decoder is disabled. And when the source data is 1, it is enabled. You guys agree with that? Next, I'm going to pick out an arbitrary destination select. So let's say I have this guy as maybe 110. I'm just arbitrarily picking out 110. Of course, destination select 2 is the most significant select line. How do I know that? I know that because of the numbering 210, 210. So that is the most significant. So I should treat this as 011. So that means that the 3 to 8 decoder is going to have that particular line active when enabled. So which line is that? Let us highlight it in yellow. Is right here. Right? So in the case of disabled, what would this be when it is disabled? When it is disabled, it is going to be 0. Right, inactive. And these are all active high outputs. So inactive would mean 0. And then when it is enabled, what would this be? Active. Perfect. 1, right? So you see this 0, 1 gave you 0, 1. So it is like you are going from 1 to this. You guys see that? It is like the same demux operation, 1 to many. Because whatever the source data was, it went straight to destination data. So when it was source data was 0, this was 0. When this was 1, this was 1. And all we had to do is select the appropriate output. Exactly the same way we do in demux. You guys see that? So a 3 to 8 decoder, we can implement using a we can use a 3 to 8 decoder to implement a 1 to 8 demux. Now on the left side, we are just showing the generic decoder with all inputs and outputs and enable as active high. On the right, we are essentially showing the same thing. However, we are showing it using the standard 74138 chip. Same concept. This guy is enabled. check. G2B connected to ground, active low input, enabled, check. My source data, earlier I just needed one input, one enable to be my source data. Right now I have G2A, my active low enable, as my source data in active low format, source data underscore L. What if I have source data in active high format? Well, just switch this around, right? Just use G1 instead of G2A in that case. The destination select, same as this. So 110, you can pick out anything. Let's say I have 010 now. Let us see what happens. All the outputs, active low outputs. Destination 0 data underscore L all the way down to destination 7 data underscore L. Active low outputs. So I'm going to start with this. I'm going to say if source data underscore L is 0, what is going to happen to the outputs? What are the outputs? Oh, let us do the easier one first. Let us do one first. I'm selecting source data underscore L as 1. What is going to happen to the outputs? All will be disabled, right? So that means that all will be 1. Perfect. Now I'm going to change this to 0. What happens when source data underscore L is 0? Which output, right? Which output is going to be active? Y2. Only the output indicated by destination select. Yes. 010, right? So 0, hold on, let's see. Alejandro, the destination select, the select lines are active high. They are active high. So you would read this as 010, right? So 010, that is the second line. So this guy will be active. Y2 will be active, and that will become active, which means 0. And all the others will remain at 1. And as you can see here, we literally took source data when it was 1 and 0, Y2 was 1 and 0. So that's how we synthesized 1 to 8 mux, demux, using a decoder. By using enable as the input data source. Which is written over here. The data is on the go pin, the enable pin. All right, so I hope you find that helpful. Let's keep moving. Now we are going to start talking about comparators. In the first studio, you guys designed a 2-bit comparator. So a lot of the discussion that is going to come up is going to be helpful in that regard, in that 2-bit comparator conversation. But we are going to expand on that. We are going to go to more bits than that. We'll talk about a 4-bit comparator as well. So all of those comparators, whether it be equality comparator or inequality comparator, they will be based on 2 types of gates. One is exclusive OR and the other one is exclusive NOR. So let us see which one is going to help us with the equality and inequality. If you observe the truth table here for exclusive OR, Exclusive OR is true, the output is true when the inputs are different. Inputs are different here, inputs are different here. So that means that this guy, exclusive OR, is a inequality detector. So it detects when the two inputs are different or not. When they are different, it gives you active, 1 at the output. Now let's talk about the exclusive NOR. And if you see exclusive NOR, the output is true when the inputs are the same. So that is equality detector. I can use this to detect whether two things are same or not. And I hope that you can also quickly write what exclusive or exclusive NOR is, right? Let us see. What is that going to be as an expression? X complement and Y complement, or X and Y, right? And for the other guy, exclusive OR, we have done this before. But I'm just doing this again over here. When X is 0 and Y is 1, or when X is 1 and Y is 0. So you have equality and inequality detector, right? We would need that to compare things. Now the exclusive OR, let's talk about the exclusive OR first. The exclusive OR gate that you see over here can come in 4 different forms, right? So what is the first one? The first one, let me use blue for this. This is exclusive OR, right? XOR. Okay. What can I say about the output here? I can say that the output is going to be true if inputs are different, right? Because it is the inequality detector. So the output will be true if the inputs are different. Does it matter if I flip the inputs? If I flip the inputs, because I'm changing both the inputs, it doesn't really matter. You still have the same condition, right? True if inputs are different. You guys see that? If you have 0, 0 here, well, if you have 0, 1 here, that indicates outputs, the inputs are different. That also means that over here, if this is 0, 1, that also means the same way, right? If you started with 1, 0 here, it also means the same way. So it doesn't matter if you have the inputs in true form or complement form. Because you are complementing both of them, it is still a valid symbol for exclusive OR. Now what would happen if you flipped one of them? If you changed one of them, one of the inputs, then the output will also get flipped, right? Because now if you started off with inputs being same, because you flipped one of them, now the inputs are the same. So the output will be inactive. After the bubble, output will again be active. So it is like saying true if outputs are different. You guys see that? Last one. It doesn't really matter which input you flip. If you flip the first one or the second one, now this becomes an equality detector. So I need to flip the output as well to keep it at the inequality detector. So all these, the 4 symbols that you see on the top are for exclusive OR gate, which means for each and every one of them, the output is true if inputs are different. Both inputs, they are different. Now let's go on to talk about the exclusive NOR. What do you have here? Output is true. True if both inputs are same. Next symbol. It doesn't matter if they are the same. All that matters is if they are the same or not. It doesn't depend. It doesn't matter if they are 0 0 or 1 1, right? So even if you flip both of them, it will still be an exclusive NOR operation. So that will still continue. Output will be true if both inputs are the same. Next, if you change one of them, as you did here or you did here, then it will become an inequality detector. So exclusive OR. So this applies even for this guy and for this guy. Right? If you change one of them, you have broken the equality. So now it becomes an inequality detector. So the remaining part here is exclusive OR. Remaining part here is exclusive OR. All right, so I hope you guys see that these symbols are equivalent. This will be helpful for a later discussion. Now, I can synthesize exclusive OR and exclusive NOR gates using NAND only synthesis. And the way you do that is by first starting, here we are doing this for exclusive OR. I'm going to try to first write the two expressions here. What do you have expression there? You have x and y complement. Over here you have x complement and y. And then of course f will be x exclusive OR. So this is and this is and this is OR. Now if I start adding bubbles like we did to change things to NAND only, what did we do? We added a bubble there, we added a bubble there, we added a bubble there, we added a bubble there. So this guy became two input NAND gate. This guy also became a two input NAND gate. This guy also became a two input NAND gate. And because I have an inversion operation here, you can see this. This is x complement here, this is y complement there. So I can combine these two inversion operations just by using this guy. Another two input NAND gate. So now you have a one-to-one mapping. Let me draw that in red. This guy same as this guy. This guy same as this guy. Both of these as this guy. And then of course that is that guy. So that's how you would convert exclusive or synthesize an exclusive OR using NAND gates. Just using those bubbles, the exercise of pushing bubbles through that we saw earlier in the class. Now we can connect exclusive OR gates in a daisy chain or a tree structure. And we are doing this to, say, for example, to generate an odd parity. So I need to talk about what odd parity is and also what daisy chain is and a tree structure is. So what is a tree structure? This guy is a tree structure. B is a tree structure. A is a daisy chain. What is a daisy chain? First you find out the exclusive OR of I1, I2. Then you add on one more input to the chain. Then you add on one more input to the chain, and so on. So that is a daisy chain structure. You have inputs I1, I2, I3, I4, and so on up to IN. So n input daisy chain structure. And you could also connect those inputs as this: I1, I2, I3, I4, and so on up to IN. So in the tree structure, first you have this, right? You have, let me use blue for this, I1, I2, I3, I4. Then you combine the outputs of I1, I2, I3, I4 to get one level. Then you have it's like a tree format, right? So you're going many to one. It's like a pyramid tree format. So with this, let us try to answer a few questions here. The first question is, why are we doing this daisy chain or tree structures anyway? Well, the reason is that exclusive OR gates have a limitation on the number of inputs. The number of inputs you can have for an exclusive OR for an exclusive NOR are two inputs. That's it. So if you have a two input situation, and you still wanted to do something like this. So if you still wanted to do I1 exclusive OR I2, exclusive OR I3, how would you do it? The only way to do it is first do these two guys, then do it with this. I1, I2, I3. But if you have n inputs, then you have these two choices in general: daisy chain or the tree structure. Now, that's the first point. That's why we are talking about this, because the limitation is on the number of inputs to the exclusive OR for the exclusive NOR gate. The next question is, do you dislike something about the daisy chain? Like, do you see some problem with the daisy chain structure? Do you guys see any issues that could come up because of deeper gate depth? You need n depending on the input. It seems like a lot of time. Okay, might you gate delays? Yeah. All right. So you guys are all on the right track here. The daisy chain structure has a really big asymmetry in terms of time, and that asymmetry increases with the increase in the number of inputs. What that means is, suppose IN changes. If IN changes, this input changed immediately. However, the other side of the input, it's going to take a long time to reflect that at the input of the final exclusive OR gate, which means that there could be some problems due to the gate delays of the exclusive OR. If one breaks, all break. Yes. That's also another problem with this. Yes. But even if everything works, you still have that gate delay problem. One guy changes instantly, the other guy changes very, very slowly. So even if the inputs, you have I1, I2, I3, say this is F, equal F, right? If I3 changes, F is going to change instantly. But you were probably not wanting that, right? So suppose you are trying to go down a truth table, and you are going from one condition to the other condition. But as you are going through that truth table, you are changing I1, I2, and I3, the changes that you make for I3 appear instantly at the output, but the changes that you make for I1 will take a long time to reflect at the output side. So that's the main problem. Timing asymmetry is a problem in daisy chain. That problem is not there in the tree structure because everything is symmetric. How about the number of gates? That's the next point. Which requires fewer gates? So let us try to see for this. Let us try to look at until I4. I1, I2, I3, I4. These four. How many gates would you need? You would need 1, 2, 3 gates, right? 3 gates to do that. How many do you have for I4? 1, 2, 3. That's it. You also have 3 exclusive OR gates if you wanted to do I1 exclusive I2 exclusive OR I3 exclusive OR I4. Yes. So if you stop at I4, you are fine. However, if you add one more, I5 for example, you would only need to add one more exclusive OR gate here. However, you will need to add 3 more exclusive OR gates over there, right? So you will have more below 4 inputs daisy chain. Yes. So if you add I5, you will have more gates in the tree structure than daisy chain. So Kevin is right. It depends on how many number of inputs you have. But in general, fewer gates, daisy chain can do fewer gates compared to tree structure on a general basis. But in some cases, it might be equal to tree structure, like we saw for I4. Now, the output of this, I've called that odd. Why did I call that odd? In order to explain that, I'm going to need an example. So I'm going to say, this is my example. I1 exclusive OR I2 exclusive OR I3. So let's see. I have I1, I2, I3, F. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 4 zeros and 4 ones. So if you did a daisy chain or a tree structure, whatever you did, what would you get for the output? F. Compare I1 and I2 first, then compare with I3, right? Or no matter what you do here, I hope you see that your outputs will be this. 0, 0, compare these two guys, what do you get? 1. Let's see here, right. So you get 1 here, here, mutually exclusive here and here. Everything will be 0. As you can see, output is 1 here, 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 and here. What is so unique about those cases? For this, I would need to count the number of inputs being true. Output F is 1 when number of input inputs 1 are odd. 1 1 1 1 1 1 3 ones, right? So if you have odd number of inputs active, your output is active. So that's where the odd comes in. So exclusive OR gate, exclusive OR, XOR, produces odd parity. Parity is one bit that indicates whether the number of ones in a sequence are odd or even. And if exclusive OR produces odd parity, that essentially means that I will have one parity bit to indicate that the number of ones in a bit sequence are odd. So let us try to do that with an example. So I will say I have a bit sequence. Say I have a bit sequence. I'm just going to make up 1 0 1 1 0 1 1 0. So I've taken a 8-bit sequence here, and I want to know whether it is odd parity or even parity. Odd / even. Which one is it? The clue is in the number of ones in bit sequence. So the number of ones in the bit sequence are 1, 2, 3, 4, 5. Odd. So it has an odd parity. Yes. Now with this, parity can be very, very helpful. Whenever we communicate between, say, a transmitter and a receiver, or whenever we store information onto a disk, then we can use this parity bit, one or maybe more than one, to ensure that we secured the data onto the disk safely. There was no corruption of data. So what you do is you generate a parity bit, you store the parity bit along with the data, and then when you want to read the information back from the memory, you also read the parity bit and make sure that it checks out. So you can use parity as a redundant bit or bits to have safe information storage and recovery. I will show you that application over here. So in this case, we have a few chips and some gates. Let us go step by step here. There is a 74X280. This is a chip that generates even or odd parity. So it is being used to generate parity based on the bit stream. What is the bit stream? The bit stream is here. The 8-bit stream. D0 to D7. So that's the first chip. The next chip is a memory chip. A memory chip to which we can read or write. The information coming in is over here. The information being read out is over here. So memory chips, I can put in information and I can read out information. And as you can see, there is a connection between the parity generator and the memory chip. So that means that I'm also storing parity and I'm also reading parity. So this parity is being stored as well. The next chip is the 74X541. That is the transceiver, 8-bit transceiver. It's a tri-state device. So when it is enabled, the inputs will connect to the outputs when enabled. Otherwise, the outputs will be in the high impedance state. Now, let us see what is happening here. Uh, let us suppose we are trying to write something to the memory chip. So let us suppose we are trying to write it, right? So let's say we have some data over here, 8-bit data, right? And we are trying to write this to the memory. So I'm going to make this guy write control is 1. And I'm going to make this read control 0 right now, right? So that's where I start. I'm trying to write an 8-bit sequence to a memory chip. So what is going to happen? Well, I would need some arbitrary 8-bit sequence. So let me pick some arbitrary bits here. 1 0 1 1 0 1 0 1. D0 to D7, I have made those 8 bits. Now, based on the bits that were chosen, the 74X280 chip will generate parity. Which one will it generate? Does it have odd parity or even parity? Alex says it has odd parity. So let us quickly count the number of ones. 1, 2, 3, 4, 5. Oh, exactly 5. So again, odd parity. If it has odd parity, then this pin will be 0, this pin will be 1. So pin number 6 is 1, pin number 5 is 0. Logic 0 and 1. Now let's move forward here. And I'm trying to write, right? So that means that this is 0, this is 1. I'm trying to write right now. These wires are connected here as well, right? And the data bus is also connected here, which means the same data is available to the memory chip, which is what? 1 0 1 1 0 1 0 1. That's what I chose. So this maps to this. Next, I am also storing parity, right? I'm also storing parity here, which means I have a 1 there. P in is 1. So I'm really storing 9-bit. So 8 bits are from the data and 1 bit is from the parity. Now tell me this. For the 9 bits, for 9 bits, parity will always be what? This is the question is for all the 9 bits. Even is right. And the reason is this. we had a case where the 8 bits were odd parity and we added one more one, so it became even parity. In the other case, if we have even parity for the data, this will be 0 in that case. So it will still be even parity. Which means I always store even parity. Right? So that essentially means always store even parity. That is for the 9 bits that we are storing, that we are writing to the memory chip. All right, now let us see if now we are trying to read things out, right? When we try to read things out, we would need this. We would need to make an adjustment. So let me make the changes, I don't know, maybe in green. I wrote things to memory. Now I want to read them out. When I want to read them out, I would make this guy 1 and I would make this guy 0. If that is 1, read underscore L will be 0, which means that these two guys will be enabled, right? I have made this guy 0, this guy is 1 here. So I have I'm reading, I'm not writing. So when I read, I'm assuming that all the bits will be read properly. So let's see what happens if I read things properly. If I read things properly, then these bits will be what? 1 0 1 1 0 1 0 1, and I will read the parity out as 1, right? And later, because this is enabled, these 8 bits will be available on the data bus. So you try to read information onto the data bus, 8-bit data bus. So when you made this enabled, all that information was available to you later on, right? So all of this will be available here. So that will be available on the data bus later on. Okay, but what about the parity? I also want to know whether there was an error or not. So let us see how that works. Notice over here, P out, the parity out was 1. Go back here. What do you have? A 1 there. How about this? Well, take a look at up. This is coming from the read signal. So this is also 1. That means this is 1. This is the read parity. With the read parity, what will it generate? You have odd parity here, right? You have odd parity here. With this as 1, you have even parity. If you have even parity, because we always stored even parity, this guy will be 1. Oh, sorry, this guy will be 0, right? It will be not odd parity. That 0 will go here when you are reading. So this is 1, this is 0. What do you get? This 0. No error. You guys see how to read this? All right, so a lot of elements over here, and I've also not talked about when there is an error, right? So when there is an error, what will happen? The read parity will indicate 0. And if this is 0, along with an odd parity number that you read, this will be 1. If this is 1, along with read signal being 1, it will indicate that there was an error, right? Error just indicates that there was a corruption of the bit when it was stored on the memory. Now, obviously, there can be 1 bit corrupted, there can be 2 bits corrupted, there can be 3 bits corrupted, and so on. But the chances of 1 bit getting corrupted are much higher than 2 bits getting corrupted. Which is why this one bit parity will be, in general, be very useful, because it is detecting for that 1 bit error. Michael says, can you explain where does P out equal 1 come from? So what did we choose? So when we were writing the information on the memory chip, because our bit stream was odd parity, we generated odd parity, right? 1. That 1 was being stored here. So parity in was 1, and when you read it, you read parity out as 1. Because you wrote 1 here, you read 1 here. So these two are the same. As are these two, as are these two, as are everything is the same here. 1 to 1. All right. So that's a discussion on parity and how you can use parity generation and checking for a 8-bit wide memory. Let's move forward. Now we are talking about equality comparators. So first we have a 1-bit comparator, and then the next one is the 4-bit comparator. So let us see if we can compare 2 bits. We have A0 and B0. By simply using an exclusive OR gate, I can find out whether they are different or not, right? The output, which is called different, is going to be 1 when these two guys are different. And it is going to be 0 when A0 and B0 are the same. So it is being used to check whether 2 bits A0 and B0 are different or not. So that's a 1-bit comparator. But it is a very simple comparator in that it is not telling us whether they are greater than or less than or equal. It is just telling you whether they are different or not. That's it. Next, you have a 4-bit comparator, also telling you whether the 4 bits are different or not. That's it. Are they different or are they not? That's it. And this can be done by checking for A0, B0, A1, B1, A2, B2, A3, B3. So think of it like this. You have A3, A2, A1, A0. Let's see. B3, B2, B1, and B0. So how would you know whether these are 2 different numbers? So you can associate numbers with them, right? Like you can say this is like 1101 with 1100, right? That's what we are talking about when we talk about A3, A2, and so on. So how would you know whether they are different or not? Well, you would say, I will have to do a comparison. I will have to do a comparison here and here and here and here. Just as you would do here, here, and here, and here. And clearly, if any one of them fails, all of them fail, right? That's why you have the OR gate here. Is the least significant bit different or not? Is the next most significant bit different or not? Is the next most significant different or not? Is the most significant bit comparison different or not? If any one of them is different, the numbers are different. So that's an example of using exclusive OR gates to find out whether 1-bit comparator for different or not works or not, the way it works. And we are also looking at a 4-bit comparator. But these are not particularly useful because they are only checking for different. They are not checking for less than, they are not checking for greater than. All they are checking for is different. that means when it is low, they are also checking for equal, right? So equal or not, that's it. So these are particularly simple. So the next thing that I'm going to do is I'm going to try to take you guys through a complete derivation of the 4-bit comparator. For this, I would need you guys to kind of uh, help me out a little bit. So when can I say A equals B? A is being represented as A3, A2, A1, A0, and B is represented as B3, B2, B1, B0. So when can I say A equals B? You probably can say that A equals B when all the 4 bits match up, right? So you would have to say something like this. A3 equals B3 and A2 equals B2 and A1 equals B1 and so on, right? Last one is A0 equals B0. Yes. How do I implement this? A3 equals B3. How do I implement that? What is my equality comparator? What is my equality detector? Which gate is equality detector? Exclusive NOR is right. Exclusive NOR is a equality detector. So I would need to do A3 exclusive NOR B3 and A2 exclusive NOR B2 and A1 exclusive NOR B1 and A0 exclusive NOR B0. Now, I don't want to write so many things so many times. So what I'll do is I'll just call this C3, C2, C1, C0. So what would this be? This would simply be A equals B if C3 and C2 and C1 and C0 is 1, right? So that's A3 and B, A equals B. Questions here? I'm just defining, let's see, I'm just defining, let's do it in blue. CK as AK exclusive NOR BK. So that's what I'm doing here. For the kth bit, the most significant bits have to match up, and this and this and this. Each and every bit has to be equal. Only then A equals B. For example, 1101, 1101. Each and every location has to match up. Next. Oh, come on. The next thing is, how about A greater than B? Now, in order to go forward with this explanation, I'll do this. 1010 or 1011 0111. Can somebody tell me which one is greater, A or B? Michael says A, and he is right. Michael, can you tell me Why did you come to that conclusion? So whoever is responding, why did you guys come to that conclusion that A is greater than B? And you did it very quickly. Compare the most significant bit first. Absolutely right. So even if I didn't have this information, even if I didn't have this information, or this information, or this information, I would be able to say A is greater than B because the most significant bit is greater, right? 53 is greater than 43. I don't need to take a look at this. If 5 is greater than 4, I'm done, right? So A is greater than B when A3 is 1 and B3 is 0. Or what if they are the same? What if your numbers are 1, 0, 1? Which one is greater? A or B? Again, A is greater than B. Because if these guys are equal, then you go on to the next comparison. And then you do the same thing as before. So what would that mean? That would mean that if A3 equals B3, which in our case is C3, so if A3 equals B3, that's the condition C3 that we defined earlier, then we look for A2 and B2 complement. Yes. And similarly, you can keep going down. If A3 equals B3 and A2 equals B2, the next one would be A1, B1 complement. And the last one, A3 equals B3, A2 equals B2, A1 equals B1, and A0 is 1 and B0 is 0. You guys agree with this? So that is essentially the complete expression for A greater than B. I want you guys to note a few things here. One is the number of inputs to the AND gate was 2 here, 3 there, 4 there, and 5 there. That's one thing to note. The second thing to note is you also had no C here, then you had C3, then you had C2, C3, then you have C2, C3, C1, right? More and more C's as you are going down. The third thing I want you to note is for A greater than B, you have A3, B3 complement, A2, B2 complement, A1, B1 complement, and so on. Those three will be helpful when we look at a block diagram next. All right. So on this slide, we have A greater than B. Earlier, we had A equal to B. Using these two results, can I somehow get A less than B? How can I write A less than B? Well, if it is not A equal and not greater, then it has to be A less than B, right? A equal to B or A greater than B, complete thing is complemented. So that means it's a NOR gate. Can I also somehow get the other three outputs that could be possible? A greater than or equal to B, A not equal to B, A less than or equal to B. Can I get that somehow using the uh, A the previous results. So let's talk about A greater than or equal to B. Well, A greater than or equal to B is simply going to be what? It is going to be A less than B complement, right? Which is simply A equal to B or A greater than B. How about A not equal to B? Well, not equal to B is simply going to be A equal to B complemented. How about A less than or equal to B? Well, A less than or equal to B should be A greater than or equal to B complement, or greater than B complement, which is what? A equal B or A less than B. What I'm trying to say here is all you need are two outputs. What are those two outputs? A equal to B and A greater than B. Using these two outputs, you can derive all the other outputs. A greater than, so A less than, A greater than or equal, A not equal, A less than or equal. You can derive all the 6 inequalities if you had those two of them. A equal, A greater than, or A greater than B, or and A equal to B. That's it. And I've given you guys the expressions to look at over here. Now let's move forward. I have a few slides over here that are essentially talking about the same thing that we just looked at. So I will keep this as your reference, and you can go through it later if you. But I don't see why you would need to. We just talked about that. We just derived these things just now. So it's the same equality comparator analysis. Then at the end you have all the summary, all the A equal to B, A greater than B, A less than B equations. Now in terms of equality comparators, you can also look at it in terms of an alternative architecture. What is that alternative architecture? You can have a 1-bit comparator here which compares the least significant bits x0 and y0, and you have a equal input and equal output. What does that mean? EQI and EQO. That means from the previous stage, am I following in the earlier comparisons, was it equal or not? If it was equal, you will get a 1. If it was a 0, that means it breaks. So at the beginning, I'm choosing 1 because so far there was nothing compared. And then I have a comparator between these two guys. It compares for equality and gives you EQ1. And if this is 1, you compare the next stage to generate EQ2. If that is 1, you compare the next stage to generate EQ3, and so on up to the n minus 1. If you start at 0, end at n minus 1, so that's a n bit equality comparator. And you're doing that comparison one after the other after the other. Now, does it matter if I do this first or not? Like, does it matter if I do this guy first or this guy first or this guy first? Does it matter if I compare most significant bits first or least significant bits first? No, it doesn't really matter. Why? Because I'm trying to check for all of them to match up, right? So it doesn't really matter which one I try to match up. So why do you think the least significant bit is being compared first? Clearly, the designers had a choice of starting with most significant versus starting with least significant. Why did they start with least significant? The least significant, because it is least significant, it has the higher chance of being different because it is changing more often. Absolutely. So that's why that they are putting that right at the front. So if it has to break, you know it very quickly because it has more chances to be different. All right. Inside this comparator, inside each comparator, you have these guys. What is that? That is essentially what? This is an exclusive NOR or equality detector. And you have the AND gate to essentially check if previous stage was equal, right? So you only do the next stage if the previous one was equal. Otherwise, it will generate 0 and it will break the entire chain. All right, questions here. All right. Remember, I told you guys that there is a diagram later on which might overwhelm you, but really, if we carefully look at the analysis from earlier, this is not a big deal. So I'm going to try to relate this diagram to the one that you had earlier, the analysis that you had earlier. So for the analysis, what did you have? Let's start with A equal to B. In this case, we had a 4-bit comparator, and A equal to B was C3 and C2 and C1 and C0, where each C is exclusive NOR gate. And exclusive NOR gate also has a few alternate designs. I'll show you that. Exclusive NOR gate can be represented as this and this and this, all four. That's exclusive NOR. Now using those two, I'm going to try to show you how this guy is being sketched. What is the difference here? We had a 4-bit comparator earlier. This guy is a 8-bit comparator. So instead of having A3 and B3, you go all the way up to P7 and Q7. What is this guy? Are you guys able to see my screen, P7 and Q7? All right, hopefully now you are able to see P7 and Q7. Is that right? So here you have Q7 complement and here you have P7 complement. There's a lag that I'm getting. Oh. All right, so Q7 complement and P7 complement, right? And now if you track those up, you will see that you have P7 complement there and P or Q7 complement there. So what are you really checking for? Whether these guys are equal or not, right? So here is the equality, P equal to Q underscore L, so active low output when P equals Q. If this is P7 complement and Q7 complement, and if these guys are the same, then flipping one of them or complementing one of them would mean that they are different. And if they are different, I can use an exclusive OR gate to find out the inequality detector. So this one is an alternate way of saying exclusive NOR. And as are all of these. So each one of them is an exclusive NOR gate. That are used to compare P7, Q7, P6, Q6, P5, Q5, and so on up to P0, Q0. So if all of them are true, what do you get? You get 1, 1, 1, 1, 1, 1, 1, all 8 ones here, right? Then you generate a 0 there. Active low output for P equal Q. You guys see that? So it is the same analysis based on exclusive NOR followed by an AND gate. And then that bubble essentially makes the output active low. Now coming to the next part of P greater than Q, right? This is P greater than Q now. And we have already established that you only need two outputs, equal and greater than. For using these two, you can generate the rest. So for that, what do you need? I go back to show you the pattern. We had A3, B3 complement or C3, A2, B2 complement or C3, C2, A1, B1 complement and so on, right? So the number of inputs were increasing, and as they were increasing, there was one input in true form, the other one was in complement form, and also there was a exclusive NOR comparison of the previous inputs. Take a look at this. For the most significant bit, what do you have? P7 and Q7 complement, right? Just as we had A3 and B3 complement. Now we have P7 and Q7 complement. Followed by, you have C7, P6, Q6 complement. Followed by C7, C6, P5, Q5 complement. And it keeps going. And then when you do the OR between all of those conditions, and then you have a bubble at the output to make the active low output for P greater than Q. So you can clearly see the number of inputs here: 2, 3, 4, 5, 6, 7, 8. I think the last one should 2, 3, 4, 5, 6, 7, 8, 9. So it keeps increasing in the number of inputs all the way up. All right. So there is a lot of lag that I'm experiencing. And let's see. So with these two outputs, there's a standard 74682 chip. We have all the 8 bits being compared available over here. P0, Q0 all the way up to P7, Q7. There are only 2 active low outputs for equality and greater than comparison. All right, let me stop the recording here because this is not going really good.